This video explores the clinical landscape of neurodegeneration, mapping the mechanical breakdown of neural circuitry in Alzheimer's, Parkinson's, and Huntington's diseases, and the targeted therapies designed to restore balance. We focus on the neurodegenerative triad, where specific circuit and protein failures lead to distinct clinical signatures, from the cognitive decline of Alzheimer's to the movement disorders of Parkinson's and Huntington's. Brain function relies on a delicate ecosystem. Neurons and various glial cells, including oligodendrocytes, astrocytes, and microglia, maintain the fragile equilibrium necessary for normal transmission. Systemic disease arises when any part of this system fails. In Alzheimer's, damage originates in the entorhinal cortex and hippocampus. Cellular pathology is defined by extracellular beta-amyloid plaques and intracellular tau neurofibrillary tangles, which collectively lead to widespread hypometabolism and atrophy. A critical challenge in Alzheimer's is the silent progression. Pathology can precede symptoms by decades. By the time cognitive decline becomes clinically noticeable, significant neurodegeneration has already occurred. Current Alzheimer's pharmacology focuses on symptom management using cholinesterase inhibitors. However, direct attempts to target amyloid plaques have largely failed to reverse cognitive decline, highlighting the complex, multifactorial nature of the disease. Movement control depends on the basal ganglia. This circuit acts as a, quote, motor control room, balancing excitatory and inhibitory pathways. Precise dopamine regulation is required for smooth, coordinated action. In Huntington's disease, a genetic mutation leads to the loss of GABAergic neurons in the striatum. This effectively, quote, shatters the inhibitory brakes of the basal ganglia, resulting in the characteristic involuntary movements known as chorea. Parkinson's disease represents the opposite failure, the loss of dopaminergic neurons. This disrupts the, quote, accelerator of the motor circuit, leading to hallmark symptoms like bradykinesia, resting tremor, and muscle rigidity. Understanding dopamine metabolism is vital. The pathway from tyrosine to dopamine, and its subsequent breakdown, underscores how environmental toxins, like the infamous MPTP case, can cause permanent Parkinsonism by destroying mitochondrial function. Treating Parkinson's involves the L-DOPA and carbidopa engine. L-DOPA crosses the blood-brain barrier to be converted into dopamine, while carbidopa prevents peripheral breakdown, reducing side effects. However, long-term efficacy is limited by progressive neuronal loss. The pharmacological arsenal for Parkinson's is diverse. Precursors boost dopamine, agonists mimic its effects, enzyme inhibitors preserve existing levels, and other agents manage secondary imbalances or specific symptoms like dyskinesia. Huntington's pharmacology seeks to manage symptoms by suppressing the relatively overactive dopamine system, often using VMAT2 inhibitors to deplete dopamine. These treatments target involuntary movements but do not slow the underlying disease progression. Ultimately, modern neuropharmacology is about balancing these synaptic levers. We have mastered symptomatic control for these conditions, yet the underlying protein aggregations and structural damage remain significant hurdles for current medicine. The future of neurodegeneration lies in moving beyond symptom management toward neuroprotection. This includes earlier biomarker detection, shifting therapeutic targets, and exploring gene therapies to address diseases at their biological source. This video synthesizes structural failure, neurochemical deficits, and targeted pharmacological interventions across Alzheimer's, Huntington's, and Parkinson's. We begin with the healthy neural infrastructure. Neurons act as the wires, while support cells like astrocytes, oligodendrocytes, and microglia manage the environment, ensuring proper signaling and immune protection. The neurodegenerative triad highlights how distinct diseases affect specific regions. Alzheimer's targets the cortex, Huntington's the striatum, and Parkinson's the substantia nigra, each with unique protein anomalies. Alzheimer's pathology involves a silent spread. Beta-amyloid plaques form extracellularly, while tau tangles damage neurons internally, leading to structural collapse long before clinical symptoms appear. Symptom management in Alzheimer's relies on the cholinergic hypothesis. ACE inhibitors attempt to boost acetylcholine, while other treatments address glutamate toxicity to mitigate cognitive impairment. The motor control network is highly complex, involving balanced dopamine signaling. Neurodegeneration here manifests as either excessive or insufficient movement, as seen in chorea or bradykinesia. In Huntington's disease, mutations lead to striatal damage. The loss of inhibitory pathways causes involuntary movements, which are managed by modulating the dopamine-heavy system. Parkinson's centers on the loss of dopaminergic neurons. Treatment strategies focus on replenishing dopamine levels to counteract tremors and rigidity. Advanced clinical perspectives emphasize identifying these conditions early. Mapping protein aggregation patterns allows for better targeting of pharmaceutical interventions. Research continues to bridge the gap between systemic deficits and cognitive outcomes, aiming for more precise, personalized approaches to neurodegenerative care. Ultimately, managing neurodegeneration requires a holistic view, combining structural understanding with targeted pharmacological support to improve quality of life. Thank you for viewing this clinical atlas of neurodegeneration. Understanding these mechanisms is the first step toward effective patient care.